Hello and welcome. My name is Max, and in this video I will present the demonstrator system that has been developed at the Chair of Integrated Systems at the Technical University of Munich in the scope of the Aramis-2 research project. The demonstrator consists of two parts: a mixed-critical tiled 4x4 system which is based on OpTiMSoC and implemented on an FPGA, and a host PC that runs the demonstrator control panel and a monitor UI showing the network on chip and the tiles of the system. The system has 15 processing tiles, which each contain an open RISC core, a local memory, and a network interface to connect the tile to the network on chip. The system uses a hybrid NoC that provides both packet switching and time division multiplexing. In the demonstrator, packet switching is used for best effort traffic, and time division multiplexing is used for critical traffic that requires latency and throughput guarantees. To demonstrate a mixed critical and globally asynchronous locally synchronous system, we defined different clock domains for the tiles and the NoC. We selected 6 of the processing tiles as critical tiles. These tiles are clocked at 75 MHz and run a pedestrian detection algorithm as an example for a critical application. The host PC sends frames for processing to the critical tiles via the I/O tile and the network on chip, waits for the result, and sends the next frame. The remaining 9 processing tiles are clocked at 50 MHz. They each run an application to generate and consume uniform random packet-switched best effort traffic as background traffic. The network on chip is clocked at 100 MHz. Protection switching is used to implement fault tolerance for the critical application. Each flit is sent twice over 2 disjoint paths. If a fault occurs on one of the paths, the flit will still be delivered on the other path. The purpose of this demonstrator is to demonstrate both the fault tolerance of the critical communication as well as the traffic isolation between the best effort and the critical traffic. First, the bitstream must be programmed into the FPGA. This typically takes a few moments, so I sped up the recording a bit. Now the host application can be started, which will connect to the FPGA, show a control panel for the demonstrator, and start a local server which we can connect to with a browser to show the monitor UI. In the monitor UI, you can see the 6 critical tiles in blue, the 9 best effort tiles in orange, and the I/O tile that is used for the communication with the host PC in gray. It is possible to inspect the tiles and individual links in the system and inject faults in the links by forcing a bit flip. The two graphs on the right show the network utilization for both best effort and TDM traffic for either a selected link or the entire NoC. Before we can start, we must load the target application into the local memory for each tile. Again, the recording is sped up a bit. When starting the system, the TDM connections are set up. The monitor UI shows the connections of the selected tile and all TDM paths that cross a selected link. Now the pedestrian detection algorithm must be trained for the image classification. In this example, we send a pre-trained dataset to the course. As the data is sent, you can see a small spike in the TDM utilization. The control panel shows some details about the number of frames that have been processed in total, the number of frames processed by each core, the current frame rate, and the detection rate. The monitor UI visualizes the utilization of the individual links. However, as you can see in the graph on the right, the overall TDM utilization is relatively low in this example. When selecting a link, the reserved slots are shown in the info section on the right. To demonstrate the protection switching, I inject a fault on the link from router 8 to router 9. As you can see, the processed frames per second are totally unaffected, which shows that the communication with all critical cores is still operational. If I inject a second fault on the alternative path to tile 7, you can see that the connection is broken and the tile no longer processes any frames. When the first fault is removed, communication with tile 7 is possible again, and the frame rate goes back to where it was before a fault was injected on the second link. Alternatively, it is also possible to reconfigure a path at runtime to bypass a faulty link. In this example, I reconfigure one of the paths from the I/O tile to tile 7 to bypass the link from router 8 to router 9. As soon as the new path is set up, communication with tile 7 is operational again. To demonstrate the traffic isolation, we generate packet-switched best effort traffic as background traffic. The best effort tiles send uniform random traffic to each other. As you can see from the utilization graph, the best effort traffic is much more uneven than the TDM traffic and causes a much higher utilization. It is important to note that in the monitor UI, a link is considered to be utilized not just when a flit traverses the link, but also when a router wants to send a link but must wait because of back pressure. For this demonstration, I create back pressure on the link from router 8 to router 4. To do this, I configure some of the best effort tiles to only send packets to tile 4. Even with just 2 tiles sending all their packets to tile 4, there already is a large increase in the utilization of this link. With 3 tiles sending all their packets to tile 4, the utilization of best effort traffic on that link reaches almost 100%. The TDM traffic has a relatively low utilization, but is completely unaffected by the contention of the best effort traffic on the link. When the critical traffic is deactivated, the utilization of the best effort traffic reaches 100%, which is indicated by the graph expanding its range on the y-axis. However, as soon as the critical traffic is reactivated, you can see that the critical traffic gets all the bandwidth it needs, which demonstrates the traffic isolation. When going back to uniform random best effort traffic, the back pressure is resolved and the utilization goes back to normal. For another demonstration of traffic isolation, I inject a fault on a link that is used by both TDM and best effort traffic. The best effort traffic is not protected against faults, which means that a fault can lead to misrouted packets and cause forbidden turns and back pressure in the NoC. Here you see that faulted packets arrive at the best effort tiles. Forbidden turns can in some cases cause deadlocks for the best effort traffic. Once a deadlock occurs, removing the fault or even stopping the best effort traffic generation won't resolve the contention of the best effort traffic. However, you can see that the critical traffic is totally unaffected by the contention. This brings me to the end of my presentation. I hope you enjoyed it. Thank you for watching and have a nice day.